Here is a review of properties of exponents from Algebra 1, including product of powers, like when we multiply the same base, we add the exponents. Power of a power is when you multiply. Power of a product is when you apply that power to each term in the product. A negative exponent means the base of your exponent is on the wrong side of the fraction bar. If your exponent is 0, your result is 1. And when you're dividing the same base, you subtract the powers. Use the properties of exponents from Algebra 1 to simplify rational exponents, an Algebra 2 concept. For part A, we have the same base, so we're going to add the exponents. To add fractions, you must have the same denominator. 1 over 2 is equal to 2 over 4. For part B, we have a product to a power. That means that this power of 2 applies to both the 6 to the 1/2 and the 4 to the 1/3. We are not distributing this power, but we will apply it to each term in the product. Now we have a power to a power and a power to a power, which requires us to multiply our powers. And 1/2 times 2 is 1, so we have 6 to the 1 times 4 to the 2/3. Can you multiply the 6 times 4? Absolutely not. This is not a 4. This is a 4 to the 2/3, which is a cube root of 4 squared. Also, in the order of simplification, exponents always take precedent over multiplication. So because you can't simplify 4 to the 2/3, then you can't also multiply it by 6. For part C, we have a product to a power. Go ahead and apply that power just like we did in part B. Multiply those exponents. Negative exponents means we're on the wrong side of the fraction bar. So this is 1/4 times 1/3, which is 1 over 12. For part D, we have a quotient with the same base, so we can just subtract the powers. 1 is just 3/3, so your answer is 5 to the 2/3. As I'm looking at part E, I noticed that I could have solved part C slightly differently. The product inside does not have the same base, but it does have the same power. So you could rewrite this product as 4 times 3, all of it to the power of 5. 5 times negative 1/5 would be negative 1, and 4 times 3 would be 12. So your result would still be 1 over 12. Let's do that process for part E. Because 42 and 6 share the same power, let's write them as a quotient all to that power, which is all still being squared. The 42 divided by 6 in parentheses is 7, and this power to a power multiplies to be 2/3. So your answer is 7 to the 2/3. For properties of radicals, let a and b be real numbers and let n be an integer greater than 1. The product property and the quotient property are just like when we were doing that with square roots. You can rewrite an nth root as the product of 2 nth roots. You can rewrite an nth root as the quotient of 2 nth roots. And you can use that to simplify nth roots by finding a perfect nth, like square, cube, fourth, fifth, and breaking it down from there. So I check my list of perfect cubes, and none of them go into 12 or 18. So let's multiply these two and then see if we can break it down. That would be 216. Oh my goodness, 216 is a perfect cube. The cube root of 216 is 6. For part B, I can rewrite it as 1 root over the quotient. 80 divided by 5 is 16, and the 4th root of 16 is 2. An expression involving a radical with index n is in simplest form when these 3 conditions are met. No radicands have perfect nth powers as factors other than 1, meaning simplify the radical. No radicands contain fractions, and no radicals appear in the denominator of a fraction. Let's simplify the cube root of 135. Because 135 is not a perfect cube, I'm looking for a perfect cube factor. There's not as many to choose from because there are less perfect cubes that are less than 135 than perfect squares. But 27 goes into 135 5 times. Rewrite cube root 135 as a product. We cannot simplify the cube root of 5 any further, and so we're left with this product. We can't have a root in the denominator, so we need to rationalize this fraction. Well, when we rationalized with a square root, we just multiplied by itself. Let's see if that works. All right, the 5th root of 64 is, I don't have a 5th root of 64. So this does not get the root out of the denominator. This did not help me simplify at all. What I need in the denominator is a perfect 5th, something that I can actually evaluate the 5th root of. Here are my perfect 5ths. Does 8 go into any of these? Yes, 8 goes into 32. So instead of multiplying by 5th root of 8 over 5th root of 8, I'm actually going to multiply by whatever gets me a perfect 5th here. The smallest perfect fifth that 8 goes into is 32. So what would I need to multiply by to get fifth root 32 in this denominator? Well, that would be fifth root of 4 divided by the fifth root of 4. Now we'll multiply by this special form of the number 1. If your roots match, you can multiply underneath. So since these are both fifth root, we can get fifth root of 28. And in our denominator, we have the fifth root of 32, which is 2. So our simplified version is fifth root of 28 over 2. For a denominator that is a sum or difference involving square roots, multiply both the numerator and denominator by the conjugate of the denominator. Remember, your conjugate for 5 plus root 3 would be 5 minus root 3. Pause this video, see if you're able to simplify on your own. Remember, when you multiply by a conjugate, that's just difference of perfect squares, which will multiply to become a squared minus b squared. Part B is a little trickier. Try it out on your own if you want, or just watch me do it. When we multiply 5 root 3 times 2 root 2, multiply non-root with non-root and root with root, so 10 root 6. Remember that 2 square root 2 squared is just 2 root 2 times 2 root 2. Now keep simplifying. When you're reducing a fraction, your negative should not be in the bottom of the fraction. It should either be in front of the fraction or distributed into the top. So here are the possibilities for your answers. And either of these would be acceptable answers. In order to simplify an expression with radicals or rational exponents, you need to have the same root and the same base. Part A is basically saying 1 fourth root 10 plus 7 fourth root 10. Because 4 is the root and 10 is the radicand, that makes these basically like terms. We treat that root term as if it's a variable. So 1 fourth root 10 plus 7 fourth root 10 is 8 fourth root 10. For part B, we have the same root and the same base, so we can combine these like terms. 2 times 8 to the 1/5 plus 10 times 8 to the 1/5 would be 12 times 8 to the 1/5. For part C, our roots match, but our bases do not. Could we simplify this cube root of 54? Only if a perfect cube were to be a factor. 27 is a perfect cube, and it is a factor of 54. So we can rewrite cube root 54 as cube root 27 times cube root 2. To simplify cube root 27, we would get 3. Now we have the same root and the same radicand. Combine. And there's our answer. Write each expression in simplest form. Assume all variables are positive. If the root matches the exponent, then you're simply left with the radicand, such as 7th root of 5 to the 7th power is 5, or the 4th root of -3 to the 4th power is 3. I'm going to begin by rewriting this product under the radicand as a product of roots. If my root is 5, I want to split the exponents into groups of 5 and then multiply what's left over. Now take the 5th root of anything you can actually take the 5th root of. 5th root of a to the 5 is a. 5th root of b to the 10 is b to the 2. That's because a root is just a rational exponent, meaning you divide those. The 5th root of c to the 5th is c. And underneath your 5th root, you still have a 4, an a cubed, and a b to the 4th. It doesn't really look much simpler, but that's your answer. Part B has only perfect cubes in it. I just separated them for us to see visually. The cube root of 64 is 4. The cube root of y to the 6 is y to the 2. This fourth root of a quotient could be rewritten as fourth root of the numerator over fourth root of the denominator. This will simplify to be x over y squared. For part D, we have a root in the denominator. Rewrite as a rational exponent. The problem is we can't have a root in the denominator, so we need to rationalize. Usually when we're rationalizing, we just multiply by the denominator and then everything's okay. But 16 divided by 3 is not an integer, which means I still have a rational exponent or a root in my denominator. So I don't know what this exponent is yet, but I need it to eventually be an integer that is greater than this existing fraction. Because 8 over 3 is 2 2/3, the smallest integer greater than 2 2/3 is 3. So my goal is to have y cubed in the denominator. If we rewrite 3 as a fraction with the denominator of 3, it would be 9/3. Now I know what this exponent needs to be. 8/3 plus 1/3 is 9/3. We have fully simplified because there is no longer a rational exponent in the denominator. You may be tempted to want to reduce the y's, but if you did that, you would end up with a rational exponent in the denominator again. So this is your answer. For part E, 14 divided by 2 is 7 over 1. X to the 1 divided by x to the 3/4 is x to the 1/4. Y to the 1/3 is still in the numerator, and z to the -6 is z to the 6 in the numerator. Because we no longer have any rational exponents in the denominator, we have fully simplified.